Hello everyone. I'm going to teach you today about the 3D stress probability transformation, how you transform three different stresses into, let's say, one plane, and also the relationship between the strains as well. So we'll start with the 3D stresses, and I will go. So you probably might have heard the, let's say this is the stress in 2D, right? So I'm pretty sure you have been working with stresses in 2D form, right? So let's say this is just shear stress, right? So if you want, you can introduce it in tensorial form. This is xx. This is y. Yx, right? Anyway, sorry, this is not sigma y, this is tau. This is the shear strain. So you know there are four components, but you know these two are same, right? So we call this usually complementary shear stress. Shear is complementary. So if you take bending moments about this point, so you know the couple exerted by these two is equal to the couple exerted by these two, right? So that the element is in equilibrium. So in 3D, you have another defined axis, let's say third axis, okay? So if you draw a cube like this, so let's say this is now sigma xx, okay? So let's call this is sigma z, third axis. So this is the direct normal stresses, normal to the plane, and there are also shear strains as well. Okay, if you take these two planes, these two are equal. That is sigma x z, right? If you take these two planes, there are two shear stresses acting on each other, and that will be sigma xy, tau xy, and you have. So I only drawn the shear stresses and normal stresses, which is possible to see, which is visible on these three surfaces, right? So the back three surfaces you can't see, right? So let's say this is a tau yz, right? Tau yz is equal to tau zy. That's why I wrote one only, right? So this is tau xy. This is tau. Sorry, this is tau xz, tau xy. Right? So you can even write this in a tensorial form, right? So this tensorial form is not a rocket science. It's how we write these as a two set of arrays, right? That's it. No, no big deal with that, right? So you can just write sigma x. This is sigma xy. So this is going to be tau x z, right? I think this should be xy. Okay, sorry about that. So this is going to be, so I write the principal stresses in this format: sigma xx, sigma y, and sigma z, right? So that I can write, this is sigma, sorry, again I wrote sigma, sorry. So this is tau x y, this is tau x z, right? So this is going to be tau yx, tau zx, tau zy, and this is going to be tau y z, right? Although there are 9 components, right? These two are equal with pair of each other, right? So that B only remains with these two are equal, right? This is actually a symmetric tensor, right? Oh, sorry. Right. So these two are equal. So that means you only have how many components? 1, 2, 3, 4, 5, 6. You only have 6 different components in the 3D format, right? You have three different components in 2D state, right? So let's do another important thing. How would you take the components in a 3D configuration, right? So let's assume if you have something like this and you have some, so neither this f vector, right? This f vector is not on any of these, planes, okay? This plane, or it's in between each 3 planes, okay? Okay. So that you can write, let's say this is x, y, and z. Okay. So let's say this vector forms an angle with respect to x-axis, let's say alpha, and this would form an angle of, say, beta. Let's say this forms an angle of say gamma, right? So you, because this alpha is in something like plane like this, okay? Where F would lie, right? So the easiest way to understand is you take two planes, right? So let's take a x, y and z. Okay, y and z. So you can take the components. So this would be f cos gamma and f cos beta, right? Y and z. So this length is f cos beta, right? So this length is f cos gamma, let's say. So you have the resultant. So that resultant, you can take the Pythagoras theorem, and this length is equal to what? F cos gamma squared plus f cos beta squared, right? And then you take that, let's say that is lambda. Okay, lambda is f cos beta squared plus f cos gamma squared, right? Similarly, you can take that lambda, right? Now our remaining axis is x-axis. So we'll get this lambda, right? Right, let's say it's another axis lambda where that resultant lies, and this is the x-axis, right? So we have something like this, that is length is lambda. So our component in x direction is f cos alpha. Again, you can make a triangle and take the length, let's say mu. So mu squared is lambda squared plus f cos alpha squared, right? What did we just do, right? We just take an f length, right? Let's say length, okay? We divided it into three components, right? We take the three components and we sum it up again using the Pythagoras theorem in two axes. Then the third axis, again we should give the same length f, right? That's mathematics, not engineering, right? So lambda is this. So you can take f out, cos squared alpha, cos squared beta gamma is equal to here f squared. So that means f squared into 1. So you can cancel it out. So we call this the directional cosine. So that shows the direction with respect to a particular axis in the 3D state. That's it, right? So whatever happens, cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1, right? So if you know alpha and beta, you can easily find gamma, right? 1 minus cos squared alpha minus cos squared beta is equal to cos squared gamma. In that way, you can find gamma. So now what we are going to do is, similarly, even in plane stress conditions, so what you need to do is, right, let's say there's stress, right? So there can be different planes withstanding different stresses, right? So that's what you did. You transform into another plane, right? Similarly, in 3D also, you can transform the stress into different plane. Now in this case, you will have something like tetrahedral. Say this is this plane you take, right? X-axis, and with the x-axis, this plane makes cos theta x, right? Theta x, let's say theta x. With y-axis, this plane makes the projection, right? Theta y. And with z-axis, let's say theta z. So what we need to do is actually, we need to convert those cubic stresses into a common plane, right? So in this case, we need the principal stress. Sorry, not the principal stress, normal stress. So this sign shows you it's coming out of this plane, right? Out of this slide. The direction is out of this slide, normal to this plane, right? Right? It's coming out of that triangular plane, right? So let's say that is sigma n. Okay. So if you use, so the derivation, you don't need the derivation, right? But you know, you can write sigma n similarly as it is. So this you don't need. Sigma n is equal to sigma x into lambda x squared. I'll tell you what this lambda x means. Okay. Sigma y into lambda y squared sigma z into lambda z squared plus 2 tau xy lambda x lambda y plus, you can take that out, right? I think yes, you can take it out. Tau yz into lambda y and lambda z. Sorry. And tau zx into lambda x lambda z, right? So this is how you take the normal stress on that plane, right? So if you are given the cubical stress state, we'll do an example. This is how you convert to the normal stress on a particular plane, right? Which makes some angle. That angle, theta x, right? Theta x gives you the lambda x as actually cos theta x, right? So we denote the lambda x as cos theta x because we don't need to write then cos again and again, right? Instead of, you can write just lambda x, right? Lambda y is what? Cos theta y. Lambda z is cos theta z, right? So what we do is actually, so if you are given something like this, right, cubical stress, there can be some plane, I don't know which angle, okay, something like this, any angle, right? So there we take the normal stress on that plane, right? Not the shear, because it's bit complex, because we can't actually give a direction to the shear in this case, right? Where it is clockwise or anti-clockwise. So that's bit complex. So I'll leave it behind for now, right? So this is the fundamental you need to understand, right? How now you have a cubical stress state, right? Stress state, and you convert it to a normal stress on any plane, right? So, okay. So if I, yes, I can go ahead. So this theta, cos theta x is lambda x, cos theta y is lambda y, and cos theta z is lambda z, right? So if you want, you can derive this using first principles, but it's not necessarily to do so. So this is the idea, okay? So what happens, right? What happens if I, let's say that normal stress, right? So if I differentiate it, right, with respect to any of these directions, right? Any of these directions, right? So that will give you the extreme points of sigma n, right? So we actually need to know if there is a particular configuration where I would have a critical sigma n value. If I talk it in Sinhala, අපිට දීලා තියෙනවා මෙතෙන්දි දැන් ස්ට්‍රෙස් එකයි shear stress එකයි normal stress එකයි shear stress එකයි මේ වගේ cubic shape එකකට. එතකොට අපිට ඒ values ටික දුන්නාම අපිට ඒක තියෙන්නේ හරියටම cube එකක. හරි. එතකොට ඒ අතර එක එක plane තියෙන්න පුළුවන්. ඒ වල normal stress එක මීට වඩා අඩු වෙන්න පුළුවන්, වැඩි වෙන්න පුළුවන්. එතකොට අපි දන්නේ නැහැ මේ stress straight එක ඇතුළෙම state එක ඇතුළෙම තියෙන්න පුළුවන් sigma n එකක් ටිකක් critical value එකක්. අපි ඒක තමයි හොයාගන්න යන්නේ. එතකොට අපි සාධාරණ plane එකක් අරන් ඒකේ normal stress එකට අපි equation එකක් ලියනවා. එතකොට අපි ඒ equation එන එකෙන් අපි බලන එක plane එකටනේ ලියන්නේ. එතකොට අපි බලනවා ඒක අවකලනය කරොත් අපිට පුළුවන් හොයාගන්න මෙයා උපරිම වෙන්නේ කොතෙන්ද කියලා. හැබැයි අපි ඒක අවකලනය කරනවට වඩා මෙතෙන්දී matrix form එකෙන් ඒක කරගන්න පුළුවන්. බලමු කොහොමද කරන්න කියලා. So it is easy since we are working with matrix forms, right? Since we are working with matrix form, we do not need to essentially use differentiation. Rather than we can use the same matrix forms to find that extreme value. So we simply call it the principal stress, right? So we need to find this common equation. From this common equation, we need to find sigma p, right? That's what we need to find, the normal principal stress, right? Oh, so the normal principal stress means what? The plane where the shear stresses are zero, right? So it's there is a plane. On that plane, you only have normal stresses. Your shear stresses become zero, right? It's not this phase, right? On this phase, you can have shear stresses, right? But we did not talk about that. What we need to do is we need to find the plane where we only have sigma p, and that would be the critical p value, right? The plane where shear stresses are zero, called the principal plane where you have the principal normal stresses, right? So that we can actually do something like this. We can resolve, okay, we can resolve the same, right? So let's say this is your principal plane. Let's say principal plane, this is okay. And Since I've been using notations, I can still use theta x, theta y, and theta z, right? Okay. So instead of resolving on a plane, so I did it on a plane, right? So I'm again resolve it in x direction and y direction and z direction, so that I can write sigma p. So we need the force, right? So there is an area component, right? So sigma p, the area of this plane. So the stress is this. The area of this plane is A. So the direction in the x direction is lambda x, right? So, and then you can write something in this way, right? Using sigma xx, right? Sigma xx, and the sigma xx into that you need to. So the sigma xx is actually the let's say this. How do I draw that? I don't know whether you will understand. Okay, so this is the x direction, the plane which perpendicular to the x direction, right? So that will have some sigma x component, right? So sigma x is also acting this way, right? Let's say, or it's the other way. Okay, no matter which way you find, which way you found, right? Let's see, it's plus, okay, negative sigma xx. So you need to convert it to a force. You need to convert it to a force, right? So that's going to be, yeah, that's okay then, right? So you have an this plus, this is into lambda x. So basically we are doing, so stress multiplied by that area gives you the force. We resolve the forces, right? So we resolve the forces, and we have a component from the shear stresses as well, right? So what we are going to do is, we can write tau y a into lambda y. So that's in y plane, right? So you really don't need this approach. So this is how we resolve for that sigma p, right? X and the a. So this is only one equation you can write in y and x direction, right? So that you can write the same thing, right? So you can write this one into this one. So you can take sigma p out, lambda x, lambda y, lambda z. So you remember this is cos alpha, cos beta, and cos gamma. In other terms, cos theta x, cos theta y, cos theta z, right? So you take it out. This is the same stress matrix that you were given earlier. මේක තමයි ඔයාලට හම්බ වෙන stress, cubic stress matrix එක අපි කියන tensorial form එක. Sigma xx to xy to xz. So did I make it right? Yeah. To yx sigma yy to yz. So I won't write these two because this one is equal to this one and this one is equal to this one, right? Because it's a waste of time writing these things again and again. So this into again lambda x, lambda y, lambda z, right? So to be 0, right? So sigma p, right? Sigma p, so we can have a solution, right? Either this matrix, this array should be 0, right? But let's check, can we have that? Because we already have cos squared theta, cos squared alpha plus cos squared gamma should equal to 1, right? So if 3 of these are 0, right? Cos alpha 0, cos beta 0, cos gamma 0. So it contradicts with this, right? So the summation gives you then 0, but it should be 1. So that means it cannot happen, right? So that you can take that out and write. So you can write this as, so you can even write this as a matrix format. So I'm multiplying this by the 3 by 3 identity matrix. Sigma p 0 p. So because any matrix can be written that matrix into the identity matrix, any square matrix, right? Minus this matrix, the whole thing into, you can take this whole matrix out. And that's it. So to obtain this solution, right? So you can, so we don't need to talk about this, right? We don't need this for now. So what we are focusing is on this, right? So you can subtract from sigma p to sigma z, so that you can write sigma p minus sigma x, and this is minus tau xy, this is minus tau xz, this is minus tau yx, sigma p minus sigma y minus tau yz, tau zx minus tau zy, sigma p minus sigma z, right? So in order to have a solution in using matrix algebra, we should take the determinant of this matrix. Let's say this is B. Okay. The determinant of this matrix should be 0 to have that solution, right? This is pure mathematics, right? So you only need the result, right? So even you don't need to form this matrix, even you don't need to prove this one, right? That this is some mathematical way how you take the solution, right? So you don't need the solution, you need the application, right? So how to take the determinant easily, right? You can write the same equation. Let's say this is A, B, C, D, E, F, G, H, I, right? To take the determinant, you write this row here, imaginary row, A, D, G, and the next row, B, E, H. What you need to do is, you have to multiply these three rows, these three, and these three diagonals, right? That is plus, that is plus, that is plus. And you can subtract, you subtract what? You subtract these three diagonals, right? You multiply this, subtract, multiply this, subtract, multiply this, and subtract. That's the easy way to take the determinant, right? So when you take the determinant from this matrix and equate it to 0, right? Equate it to 0, you will obtain a solution like this, right? That solution is, you can write this as sigma p minus, let's say, I1 p squared. So this sigma p is principal stress, right? I2 p minus I3 is equal to 0, right? So this is how you write that equation, right? When you simplify this, you will obtain this. So this I is actually this I1 is sigma x, sigma y, sigma z. I2 is what? Oh, that is sigma x, sigma y plus sigma x, sigma z plus sigma y, sigma z minus tau xy squared tau yz squared minus tau zx squared, right? So this is right. So, and I3 is a huge matrix, right? So I will write it. So no, I will tell you what it is. Actually, you are getting the determinant of stress what is this? So when you simplify it, right? So when you simplify it, what it tells you, for I3, it gives you the determinant of this same stress matrix that is given to you, right? Determinant. Sigma 3 is exactly the determinant of that matrix which is initially given to you. And say I2 is this, I3 is this. We call these stress invariants. Why we call this stress invariants? Because these are independent of your coordinate axis, right? Whatever angle you rotate, right? This will give you the exact I value because these are dependent on your theta values, right? Can you see? So if I talk it in Sinhala, මේවට අපි කියනවා stress invariant කියලා. මේ I1 I2 I3 කියන value තුන ඕගොල්ලන්ගේ plane එක මොන විදියට කියන්නේ ඕගොල්ලෝ cubical stress එක අපි plane එක මොන විදියකට හැරෙව්වත් right අපි මොන coordinate මොන plane එකක stress එක ගත්තත් මේවා ඒ coordinate එක මත depend වෙන්නේ නැහැ. ඒවා දෙන්නේ මේ value තුනමයි. ඕගොල්ලන්ට පේනවද ඒක අපි හරවන්නේ theta x theta y theta වලින් ඒවා මේ වලින් ස්වායත්තයි. එතකොට ඔයා එක plane එකක ඔයා ගන්නවා කියනපුවා අපි sigma p normal එක. හරි. එතකොට මේ sigma p එක කියන එකට I කියලා එකක් එනවා. principal stress එකේ stress variant එක I කියන එකට මේ value තුනමයි එන්නේ. ඔයාගේ matrix එකක් දෙනවනේ මුලින්ම. මෙන්න මේ stress එක. එතකොට ඒකේ තියෙන values ටික වෙනස් වෙන්නේ නැහැ. අපි මොන plane එකට ගත්තත් ඕවා independent. right. මොන විදියට හැරෙව්වත් එච්චරයි. ඒකයි අපි invariant කියලා කියන්නේ. හරිද? එතකොට give you the same number, right? Whatever you plug in, right? Whatever you plug in, it gives you the same number, right? So you need to do actually an example, right? Stress invariants basically tell you express, right? If these are expressed in terms of different coordinate systems, right? But these are actually independent, right? I1, I2, I3 are independent of the coordinate you take. That's it, right? We'll do an example. Yes, we can go into, sorry, different slide, I think. Sorry. So we can go into this stress state. So you have been given this stress state 12 minus 3 5 3 7 10 5 so these have been given actually like a cube, right? So you can imagine the sigma xx is 12, right? Sigma yy is 7, sigma 11, sigma z is actually it's a compression. Tension is positive, right? It's in the other way 11, right? Sigma xy. So xy is this one, right? These shear stresses is 3, right? And this is sigma xyz. So these are some stress state. So now you need to find the stress invariant, right? So stress invariant, right? So you remember I1, right? I1 is what? So I need to erase this matrix. Give me a second. So I1, and so the I1 is what? Sigma x, sigma y plus sigma z. So that is sigma x plus sigma y plus sigma z, right? So that's gonna give you what? So we are going to find, so we need to solve this equation in order to find sigma phi, p, the principal stress, right? Where did we get the equation? From the matrix calculation, right? Matrix algebra. So in order to find the solution, determinant should be 0. When I set the determinant to 0, it gives you this solution, right? So that I1, I2, I3 are the stress invariant. So we have to find those and then plug into the equation and solve it, right? So we have to solve it. I1, I2, I3 is what? 19 minus see, that is 8, right? So I2 is sigma x, sigma y, sigma x, sigma y, 12 into 7, it's 84. And then sigma x is said 12 into minus 11. And then 7 into minus 11. Sigma y is minus tau xy squared minus squared minus 5 squared minus 10 squared, right? So that will give you a value of minus 259. I would say, let me check it again. 12 into 7 is 84 minus 132 minus 77 minus 9 minus 25 minus 100. Yeah, it's minus 157. So there's I2. So I3 is the determinant of this matrix, right? So this determinant and this determinant is not the same. Here you have, it's obtained from sigma p minus this matrix, right? So those two are different. Keep in mind. So this matrix, you can take the determinants from your calculator. So I can't show you how to do is, I'll tell you the step. So I hope you have Casio FX991 ES plus or some sort of familiar calculator. So you need to switch on your calculator and there's a button called mode, setup mode or setup. So you can press mode and that shows you different modes, complex stat, equation. So in that 6 one, it's matrix, right? So you can press 6. Then it asks mat A, mat B, mat C. So you mat A is number 1, right? So you press number 1. Then it asks 3 by 3, 3 by 1, 2 by 2, likewise, right? So you have to give 3 by 3 matrix. So you press again number 1, right? According to your 3 by 3 matrix, right? So it asks the value. So you have to simply type the value and press equal, right? So I type 12 and equal and then type minus 3 because it type by row, right? Minus 3 and then 5 and minus 3 and 7, 10, 5, 10, minus 11, right? So once you give the final value, press the orange color AC button, right? AC. don't worry, nothing will happen. Just press the AC button, right? Then everything, you see a 0 mark in, but you can now go to matrix mode. So you need to press shift button. You can see the left top of the corner of your calculator, shift button. Press shift, and then you need the matrix button. So you can see the above number 4 button, right? You have some written in yellow color matrix. So you can press number 4. What I did was I press shift, then number 4, right? So then it asks the matrix or determinant, likewise something. So I need the determinant, right? So I press, so there's called something called dit, right? So it's 7. I press 7. So then it gives you dit. Then open a bracket. So again I press shift and 4. It gives you which matrix you need the determinant. So I need matrix A. That's number 3. So press 3 and you equal it. So that gives you 2500 minus, right? So now you have the equation. So that's given by sigma p square, sigma p cube minus 8 sigma p squared it's again minus sigma p and minus. So that's going to be I3 is minus, but you have minus I3, right? Minus I3. So that's going to give you plus 2500. So you need to solve this equation to find sigma p, which is your principal stress. So this is a cubic equation which will have 3 roots, right? So again, you can solve this using your calculator. So press mod and you need to go to equation. It's number 5. So then it asks which type of equation. So our equation is type 4, ax squared plus bx squared plus cx plus d equals to 0. So press number 4. Then it asks the coefficient. So my first coefficient is 1. Second coefficient is minus 8. Third coefficient is minus 259. Fourth coefficient is 2500, right? And I press equal, so it will give you the values. That's sigma p1. Let's call it sigma p1. So that's minus 16.6. Sigma p2. Again, you press the button. Okay, so that will give you 13.4. Again, you press the equal button. That will give you sigma p3. What's that? 11.2, right? Yeah. So you need to draw this in a Mohr circle, right? So I'll take this. Sigma 1 is the principal. So I take the tension positive, right? Principal stress. So sigma 1 is this one, right? Sigma 1. It's the largest tensile stress. So this is sigma 2. And this is sigma 3. Compressive stress, right? So you can draw it according to this, right? Sigma 1 is 13 point something, right? let's say it's here. So sigma 2 is 11 point something. So you know principal stress occurs where the shear stress is 0, right? On that plane, right? Sigma 2 and sigma 3 is minus 16 point something. Right? So you can draw the curve for these two elements. And I don't think my circle is good. So you need the exact circle. And then the circle width. So this will give you the 3D Mohr circle. So you know the values, right? This is 13 point something. 4. This is 11.21. And this is what? 16.6, right? So this is sigma and tau. Principal stresses are always act on x-axis because the corresponding tau is 0, right? That's the fundamental definition. So with that, we will go with the strain, right? So actually, let's take a small example like this. So this is the initial element, right? Let's say you have a different state due to it's deformed, right? Okay. It's deformed. Let's say a plane in this direction, theta, right? So this is delta x, this is delta y, the original length, right? So let's call this x dash axis and the perpendicular axis y dash. This is x and y. So what we are basically doing is we transform the strain. So we are going to transform the strain. In the previous example, we transform these stresses into a particular plane in 3D. So we are still doing in a 2D form, right? Because we can combine with its 3D form, right? So what we need to do is this is sigma x. So the deformed shape gives you, this is the length change. So you can write the length change, let's say delta over original length is called the strain in that direction. The deformation with respect to the original length, right? So if I write it, the total length, so delta is epsilon naught x into delta x, right? Okay, so you can write the total length, right? Total length you can write delta x plus this delta. This delta is epsilon x into delta x. You can take delta x out and write 1 plus epsilon naught x. And similarly, you can write, so you take, this is the deformed, so this is the original, right? So let's say this is delta s, okay, the plane we are talking about, right? So now the deformed shape gives you something like this, right? So this length is the delta S in that strain, right? So this is right. Let's call this not this one, because this element now it's like this, right? So that length change, right? The total length you can write similar to this delta y, take out epsilon plus x direction, so y direction. This you can write the total length. You can write delta S 1 plus epsilon S, right? So you can take this triangle and take the cos rule. So you know the cos rule, right? If it is ABC, let's say theta. So I don't really remember what is cos rule. So that will give you something like B squared plus C squared minus 2BC cos theta is equal to A squared. As I remember, this was the cos rule, right? I don't really remember this is plus, so negative. As I remember, this one is correct, right? B plus C, yes. So your A is this, B is this, and C is this, right? So when you plug it, you can obtain an equation like this. Epsilon naught is, so that is the epsilon naught strain in some angle theta, right? Some plane, some direction, which is theta angle to the x direction, right? So that is given by epsilon naught x cos squared theta plus epsilon y sine squared theta and gamma xy sine theta cos theta, right? So you can make this cos squared theta is 1 plus cos 2 theta over 2, right? This is 1 minus cos theta, cos 2 theta over 2, right? This is sine 2 theta over 2, right? So when you plug it, you can write, so actually this is epsilon x dash, right? Because that's a plane, right? So epsilon dash you can write, when you simplify, then it's using cos 2 theta and right sine 2 theta, you can write like this, sigma x plus sigma y over 2 into cos 2 theta and plus, this is very important, this is gamma xy over 2, right? Because you usually draw this Mohr circle of strain on epsilon and gamma x by 2 axis, right? Mohr circles of strain, remember? So you can plug this value, right? So this is 90. So if you, instead of theta, if you plug 90 plus theta from, because this theta is measured from the positive direction of x. So if you plug theta plus 90, so this will give you the strain in this direction, right? Strain in this y dash direction. So instead of theta, you can plug 90 plus theta, right? So that will give you, this is not going to change. So this comes, so this would be minus cos 2 theta. This is going to be minus sine 2 theta, right? So we'll just, sorry, this is strain on y. So we just add these two plus, so these will be cancelled. So you will be getting, this is very important. So what does this tell you? Sum of normal strain remain constant regardless the rotation angle. Sum of normal strain, so this is normal strain. So this is the shear strain gamma xy, right? The shear strains we took the normal strain, okay? Normal strain along that direction. So that's fundamental. So sum of normal strain, right, remain constant regardless the rotation angle, right? So these are two perpendicular axes. These are two perpendicular axes, right? So that this will give you, so let's say this is x, y, z, we will call ABC, okay? So, okay, I'll call this x, y, z, okay? So this will give you, see, epsilon x. So with Poisson's effect, right? So you know when the length is increased, so your volume is going to decrease. So when your specimen is stretched, right? Stretched up to this level, right? So it will reduce its thickness, right? So we will address that strain as Poisson's ratio, longitudinal direction, the ratio of longitudinal strain and lateral strain, right? So that will give you, so sigma x, let's say, so this is the Young's modulus. So this will give you sigma x minus tau, sorry, mu, that's a Poisson ratio, sigma y plus sigma z. So this is how your stress is. So this is nothing but how the strain is related to the stress in three normal directions, right? So you can switch the variables and write the same expression. There's a pattern, right? Sigma y, that's Poisson's ratio, sigma x plus sigma z, right? And sigma, sorry, sigma not epsilon, epsilon is said, stress is going to be E sigma z minus Poisson's ratio into sigma x so this give you sigma y. So this tells you how the strain, normal strain, is related to the normal stress, right? Along these three main directions, right? Perpendicular. So these x, y, z are perpendicular axis. So we are usually working under plane stress conditions. So what do you mean by plane stress? So that gives you, so in one of your plane is just a surface, right? So you are in a surface, right? So you are actually in a surface where the stress along the third axis is 0, right? Let's say something like this, right? So where you have sigma, so you have xy plane, but the sigma z is 0, and that comes under plane stress conditions. Let's say this is 0, okay? 0, 0, 0. This would give you a very important result. Let's say your sigma z is 0, but have a look at that epsilon node z. Even if your stress in the z direction is 0, your strain in the z direction is not 0, right? This is very critical. Okay, so plane strain means another topic, right? So that's different. We are working under plane stress. So your stress simply in the third, any of the three axes is 0, right? So you are working under 2D stress, right? 2D state actually, but your strain is there, right? Strain is essentially in all three normal directions, right? So this will give you normal strain, right? So that, so you can, so this will give you epsilon naught is how epsilon is related to the stressor. So we can simplify and write some equation to the stress as well. So if you write it, we can write, so we can write the same expression as this epsilon is, so using this sigma x sigma y, you can find this, you can plug it here, then you can write mu over 1 over mu this is valid under plane stress condition, right? Okay, so this equation you can use under plane stress conditions, because then you have how the epsilon x, epsilon I and epsilon z is directly related, right? If I talk it in Sinhala, මෙතන තියෙන්නේ strain එක විතතිය කොහොමද stress එකත් එක්ක වෙනස් වෙන්නේ කියලා. normal direction තුනේ. මෙතන තියෙන්නේ තව අනිත් direction එකේ විතතිය. අපි තාම දන්නේ epsilon x උයි epsilon y epsilon z උයි කොහොමද relate වෙන්නේ කියලා. ඒක තමයි අපිට මෙතනින් එන්නේ. ඒකට ඕනේ අපිට මෙන්න මේ sigma xy sigma x yy. එතකොට sigma x sigma y හොයාගන්න පුළුවන් අපිට මේ equation දෙකෙන් ෆන්ක්ෂන් එකක් විදිහට epsilon x ගේ epsilon y ගේ. ඒ දෙන්නා මෙතෙන්ට දැම්මම අපිට මෙහෙම equation එකක් එනවා. හරිද? මේක මතක තියාගන්න අපි plane stress condition වල ඉන්නේ. plane stress කියන්නේ අපේ third axis එකේ stress එකක් නැහැ. හැබැයි strain එකක් තියෙන්න පුළුවන්. කියන්නේ අපි axis තුනක් ගත්තොත් එක කියන්නේ එක plane එකක විතරයි stress එක තියෙන්නේ, right? xy කියලා ගන්න plane එකේ විතරයි stress එක තියෙන්නේ. out of plane එකේ stress එකක් නැහැ. right? So අපේ out of plane එක මේ වෙලාවේ අපි ගමු z axis එක කියලා. So we will move with if you need, you can even find this sigma x as well, right? So sigma x you can write like this. X epsilon y, right? So these two are very identical, right? It depends on to whom you use the Poisson's ratio, right? For epsilon x, you use the Poisson ratio to epsilon y. For sigma y, you use the Poisson's ratio for epsilon is x, right? So you know you are working under plane stress conditions, so your sigma x is out of plane stress is 0, right? So actually, it's like this. So in your Mohr circle, you remember sigma x. This is the shear strain, right? Shear stresses. Sigma x, sigma y. What the plane stress assumption is, right? So sigma z is what? 0. So you only reduce it to a plane, right? So we'll do an example. Actually, there are something called strain rosettes to calculate the strain in any particular sample, and it gives you, let's say, so we have an object special equipment. It's called strain rosette to calculate the strain on an object along that direction, right? Let's say an object like this, right? So strain rosette, what it does is it has some coil, right? So it gives you the strain along that direction, right? So this is glued to the object, and when the length is, let's say, increased or contract, this coil will stretched, right? So you know R equals rho L over A, right? So when the length is increased, you know the volume of this coil gets decreased. It's Poisson's ratio, right? So that this resistance will increase, right? So based on the resistance, it measures the strain, right? So these three are actually, if three rosettes are given in this way, right? Right. It can measure the epsilon naught in that direction. So how we get this epsilon naught, right? Based on this theta. You remember the first equation we derived? This one, right? Based on the angle of the strain rosette with respect to the positive direction of x, right? Angle always measured from the positive direction of x, and that will give you the strain in that way, right? So this is given by the strain rosette, right? So you can compute it the sigma x and sigma y, right? So what we are going to do is, first we'll do an example like this, right? So this given you an example, the delta strain rosette is mounted on an aluminum piston shaft on the figure below. So the following readings are obtained from each gauge. Poisson's ratio is this, Young's modulus is this, epsilon naught A, B, C is this, right? So if that there are some strain rosettes in 45 angles. In that case, you can specially derive the gamma xy is also as an equation. I'll leave it you to work it out. So I'll do this example and show you how it's done, right? So we have, so it's simple, right? The epsilon x dash is given, right? We know theta, right? We know theta, and we just need to calculate, right? We just need to calculate what is the value. Yeah, these values epsilon x, y, z, right? So if we draw xy axis, right? This is, let's say, horizontal positive x-axis, right? So this is 90, right? So this would give you 30 minus 90 plus x, and we'll draw it like this, right? So this angle is, what is that? Is that angle 90 plus? So if call this y-axis, this is 90 plus 8, that's going to be 98, right? That's going to be 98. Okay. So what's the other angles? So if this is 120, right? So this 120 is measured from this, right? So if this is 98, so this will give you 22, right? It doesn't matter, because even if you calculate this angle, that is same as minus 22. That's something to deal with trigonometry. And if you need this strain angle, you should get this angle, right? But that you can extend it up to here, and this would give you so this would be 38, right? Okay, so we need to plug it into this equation. Theta is known, and find the epsilon x values, right? So I'll write that epsilon a. So a is what? 820 is equal to something into cos 98, right? So you have some equation, right? And I won't write it because you have to write it. Mu sigma x. So is it sigma x? No, sorry, epsilon of x. This is epsilon naught x into something, then epsilon y into something plus gamma xy into something. So this is epsilon x into cos something into minus 38, right? The second one. And you will have same 98 here, right? Here you will have minus 38. So basically you have to apply this one, theta. So your 820 is epsilon naught x cos squared 38 minus plus sines epsilon by sine squared 38 plus gamma xy sine 38 cos 38. Epsilon b, that is minus 150. That's going to be epsilon x cos squared minus 38 plus epsilon y sine squared minus 38. Sorry, the first one is 98, right? 98, 98, 98. So the second one minus 38, minus 38, minus 38. So third one, sorry, again wrong. 98, 98, and 98. This is second one, 38, 38, and 38. For the third one, minus 22, minus 22, minus 22. In that way, you can form 3 equations, right? You can form 3 equations and find sigma x. So that's the stress in x and y, strain in x and y direction, and the shear strain that will be given. What is the strain? So the strain will be given to you like minus 220.7 mu 754 mu. This is, yes, okay. So now you can, so now you know what, so you have found these three. It's okay, it's done, right? So you need to draw this using, okay, find the principal stresses, right? So more circle you have to draw it, right? Okay, so if you draw it using a more circle, right? So I already told you, you draw it right. This is gamma x by 2, right? So y by 2. This is psi, right? Okay. So actually this is gamma by 2, right? Whatever I call it, gamma by 2, right? Epsilon naught x, and this is going to be, so your major one is 700, and so that's going to be 754, right? My Cos Strain 754. So that's on this line. Let's say this is 754. So whatever point that will appear here, right? So these are not principal strains. These are stresses in x, y, and say, sorry, x and y directions, right? So, and the next strain would be minus 220. This one, right? It's minus 220, right? Minus 220, and you, so before that we have an important step. Actually we are not robots, right? So sometimes we are being taught, okay, if your principal stress is this, take the direction of shear stress at that, right? So we actually do not need that, right? We can take it from the, even from the first principles, because just have a look at these strain values. Sigma is x is negative, sigma y is positive, and gamma xy is negative, right? Just keep in remember, it's like 200, 700 and 600 something, right? So let's plot an original. So this is your original element, right? So what happens is, in x direction, you have a negative strain, right? So that means your element has contracted in x direction. It's like this. So definitely, so then it should elongate in y direction, right? This is only with your x and y strains, right? So y direction it elongates, x direction contracts, right? But you have a shear in strain as well, right? So what's the direction of that? It's negative, right? So we plot the shear strain in this way as positive, right? In this way as positive, right? But let's check, right? If you have some element like this, you are stretching it here while you are compressing it here. So it would more likely to rotate along this axis to here or here. Probably it would rotate about this, right? To this direction, right? So that's quite practical, right? So that your element would be actually like this. Right? No, it's not actually like that. This is the axis and there's a shearing strain, okay? So the element deforms like a parallelogram, right? So your element would look like this. Right? So it's a shear strain, right? So the element rotates, right? So this is the axis. So let's say like here, you can see rather than this distance is large, right? So it will give large normal strain along that direction, right? Compared to the original direction that is given to you, right? Okay. So we need to find the principal stresses, right? Principal stresses is maximum, sorry, principal strain, the maximum strains, right? Maximum strains where the shearing strain is almost zero, right? So for the principal strain, right? So you can even see from your knowledge, right? So if I recall it in Sinhala, so මෙතන ඕගලන්ට පේනවා මෙතන එලිමන්ට් එක මේක තමයි ඔරිජිනල් එලිමන්ට් එක. හරි. එතකොට ඕගොල්ලෝගේ පේනවා ස්ට්‍රේන් එක x ඩිරෙක්ෂන් එකේ නෙගටිව්. ඒ කියන්නේ එයා x ඩිරෙක්ෂන් එකේ length එක අඩු වෙලා තියෙන කන්ට්‍රැක්ට් වෙලා. ඒකම අපිට පේනවා ඒ වොලියුම් එක තියාගන්න. එයා y ඩිරෙක්ෂන් එකේ ඉලොන්ගේට් වෙලා තියෙනවා. ඔය රේෂියෝ එක තමයි ඔය ඉලොන්ගේෂන් දෙකේ රේෂියෝ එක තමයි අපි කියන්නේ පොයිසන් රේෂියෝ එක කියලා. හරි. longitudinal strain එකයි lateral strain එකයි රේෂියෝ එක. එතකොට අපි කියනවා මේ දැන් ඕගලන්ට පේනවද මෙතන ඉඳන් දැන් මේ එලිමන්ට් එක ඇත්තටම දැන් shear strain එක උත් වෙලා තියෙන. එයා එලිමන්ට් එක මෙන්න මේ වගේ පැත්තක තමයි දැන් තියෙන්නේ. හරි. මෙහෙම අවස්ථාවක තමයි දැන් මේ එලිමන්ට් එක තියෙන්නේ. එතකොට ඕගලන්ට පේනවා මෙතන ඉඳන් මෙතනට තියෙන දිග බලන්න. ඊට වඩා මේ දිග වැඩිනේ. එතකොට මේක තමයි ඕගලන්ට දීපු ඇක්සිස් එක. හැබැයි මේකේ තියෙනවා ඊට වැඩි ස්ට්‍රේන් එකක්. මේ පේනවද? දිග වැඩි මේකේ. මේක දිගට වඩා මේක දිග වැඩි. කියන්නේ මේ වගේ ඇක්සිස් එකක් ඔයාගේ ප්‍රින්සිපල් ස්ට්‍රේන් එක තියෙන්න පුළුවන් නේ. ප්‍රින්සිපල් ස්ට්‍රේන් එක කියන්නේ ලොකුම ස්ට්‍රේන් එකනේ. shear strain එක බිඳුව වෙන. හරිද? එතකොට අපිට ඕනේ අන්නේ ප්ලේන් එක ඇන්ගල් එක හොයාගන්න නේ. එතකොට අපි ඒක තමයි මෝ සර්කල් එකෙන් ගන්න. මේක ඔළුවේ තියාගන්න හැමතිස්සෙම. එතකොට අපිට පේනවා මෙයා මෙතන ඉඳියොත් එප්සයිලන් y කී ඉඳලා මෙයා යන්න ඕනේ ඇත්තටම මේ ප්ලේන් එක හම්බ වෙන්න ඇන්ටි ක්ලොක්වයිස් ඩිරෙක්ෂන් එකක. right? මෙයා මේ ස්ටේට් එකේ ඉඳන් ඇන්ටි ක්ලොක්වයිස් ඩිරෙක්ෂන් එකේ ගියාම තමයි මේ ප්ලේන් එක මුලින්ම හම්බ වෙන්නේ. ඒ වගේම අපි ඊට පස්සේ ගමු අපි මෝ සර්කල් එක ඇන්දොත් let's go to the Mohr circle. Yes, here. So now you have a problem whether to mark it here or here, right? Whether to mark it from here to here, right? So it's, or remember it's gamma over 2, right? So that's going to be something around minus 308, right? You have to mark. So let's say you remember this was sigma y epsilon y, right? So from that you have to go anti-clockwise to meet that. So let's say if you are here, you have to go clockwise to meet your principal stress. Principal stress or principal strain always lies in this axis, right? So you have to go in clockwise direction to meet. But if you are here, you have to go in anti-clockwise, right? So that gives you, so this should be your point, because in here you have to go anti-clockwise to meet the direction where you have principal strain, right? Because how you get is, because this is from your thinking, right? So rather than this strain is quite large, right? So there's more possibility to have principal strain on that kind of a angle, right? So that I think I have to smaller this graph, right? So this point would lie here, right? Minus 308. So you have to, if it is dark, the way it's, that is also you have to go anti-clockwise, right? To meet the principal strain, right? So because these are in a diameter, right? If one point is located, otherwise other one is easy. So this would be your diameter. So this is your circle. Right. So from this you can take the, so this would, I would say this is your principal strain. Let's say epsilon let's say P1 and let's epsilon P2, right? So this is, let's say, R radius, right? So you can determine this point using geometry. So you need to xy, you need the coordinates of xy. So this is going to be x1 y1, x2 y2. So this is going to be x1 plus x2 over 2 and y1 plus y2 over 2, right? This coordinate. And from that coordinate, you have to add the radius to obtain the epsilon naught 1, right? So I'll call this A and B, okay? You can find A plus radius, right? A plus the radius, okay? This is A minus the radius, okay? That will give you the principal strain. So that I think your values are, so this would give you something around 843 and 309, right? So these are the in plane principal strains, right? In plane principal strains, like we called these three, right? In plane strain. This is the out of plane strain, right? These are the in plane principal strains, right? in plane principal strains, right? So now we found these are the in plane principal strains using Mohr circle for strain. Then find the principal stresses. We can do that as well, right? Principal stresses. How do I find it? So you can go ahead. So if you want, you can calculate the out of plane principal stress as well. Set using this equation, this one. So you know principal stresses, so principal strains, 800 and something and 309, and mu is 0.3, 0.33, I think. So you can plug in and I think it would give you some value as minus 266. You better check it. This is minus 0.33, sorry, 0.33. This is 0.33, and this is 0.33, and this is 843, and this is minus 309. Right, this would give you minus 360. This is the out of plane strain, right? Out of plane principal strain, right? These are in plane principal strains, right? This is valid for even. So these are the planes where the shear strain is 0, right? So that now it's done, right? So now you can write so can you see this can you see this epsilon x plus epsilon y? See, these are the principal stresses, something like epsilon dash epsilon. So epsilon x and y, what are x and y? That is this, right? But we have a principle, what? The sum of normal strain remains constant regardless of the rotation, right? So even if you plug these values, epsilon naught x plus epsilon y is equal to the summation of principal strains as well, right? Epsilon x dash p1 epsilon p2, right? So 842 43 minus 309 will give you 700 and what, 54 minus 220, right? So that's going to give you something around, I don't know, 500 something, right? So yes, 534, right? Because even from this stage, right, from this stage you can find the out of plane strain, right? Out of plane strain. So these are the in plane principal strain, right? In plane principal strain, sorry, I call it, I think, out of plane principal, not out of plane stress, right? Because we found the Mohr circle, and from that we obtain the in plane principal strain, right? And from there you need to find the principal stresses, right? So how can you find principal stresses? So if you have the principal strains, right, so you just need to plug into the values, right? So there's this equation, right, and this equation, principal stresses, because you know the principal strains, right? Along that direction you have the principal stresses, right? So you can find principal strain in x direction right? Sorry, this is 3, 3. Oh, well, sorry, this is E, right? 10.4. This is the equation. Okay, I'll show you again. E over 1 minus mu squared epsilon naught x plus epsilon naught y. So if you need x, you need x, right? Three squared. So epsilon x is what? X is what? You can't actually say this is x, okay, because these are not in the x directions. Principal stresses now. Since we have principal strains, let's say epsilon 1. So our major principal stress is 843. Okay. Plus would give you something around 54, right? This is the stress. So sigma 2 would give you right. Sigma 2 is actually what? So you can find, let's say it's the second principal stress. Okay. So that would give you something around 339. So this is your second principal stress. So sigma 3 is what? We are in plane stress conditions, right? So that's 0, right? So yes, you can even draw this using a Mohr circle. How? So this is 844 and shear strain is 0. Shear stress is 0. Shear stress 806,000. And you have minus, and another one is 0, and you have minus 339. So these are your 3D Mohr circles. So always keep in mind, right? Always keep in mind to draw something like this and see what actually happens rather than being stereotyped, right? So with this, we did these examples, right? We did this example. We have already drawn the Mohr circle as well, right? Mohr circle for stresses, we draw it. Yes. Thank you very much.